Brignall. We will be speaking on modular decomposition and graph reconstruction.
Thank you very much. I ought to start, I suppose. Some of you might be wondering why there's a slightly random British mathematician on the agenda. Let's talk about something slightly random. Perhaps it can be explained by my birthday greetings to Doron. Just start with birthday greeting. It makes sense actually to talk backwards in intending of talking. That means you get your results even if you run.
Robert is my first academic grandchild.
Oh, you've given the game away. Happy birthday, Grandpa. All right, okay. So I'm going to talk about graph reconstruction, which is a reasonably famous conjecture that's been floating around for a very, very long time.
Could you use a darker marker?
Unfortunately, it's quite hard. So to see. I should say this is
try to talk louder. Yeah, shout.
Yeah, I can shout, that's all right. I should say this is joint work with a couple of colleagues, well, a former colleague in Bristol and an existing colleague. So that's Nick Georgiou and Rob Waters.
Darker marker, yeah.
Okay.
Can you use a darker marker, please?
Yeah, I've not looked at this one. That's darker.
Thank you.
Perhaps. Okay, so we all know what a graph is. The deck of a graph, oh no, look at that, is the following thing. It's really a multiset, so maybe I'll use magma notation to denote it as a multiset. It's a set of graphs, subgraphs of G, and you've had a vertex deleted from. So, and the reconstruction conjecture is very simple, for those of you who've never seen it before. All it says is that every graph which has at least 3 vertices, you can see why, you can have a go yourself, see why it doesn't work with 2, can be reconstructed given just this set, or this multiset. Write that up. So it's uniquely determined by its depth. So this comes from, traditionally well, the conjecture was made by Ulam in 1960, but actually the first result on this is that all trees are reconstructible, and that's due to Kelly. He did that in 1957, so and he makes a comment at the end that maybe this is also true. So the conjecture is probably really jointly true to these, but it's always attributed to Ulam. Okay. Some other results in the field. This is still essentially wide open. Many people have had a go and failed. And I think Nash Williams talked about it being a sort of infectious bug. People are getting infected with the bug of graph reconstruction. And then it takes over their lives and they ruin their life by trying to improve this.
I forget whether these graphs are vertex labeled or not, or doesn't it matter?
It doesn't really matter. Well, no, they're not going to have labels. If they're labeled, it becomes quite easy, because you can recognize which vertex is deleted. Yeah, so they better be unlabeled. All right, so some other results. This one looks kind of promising. Olabash, I think, in 1990, found it was true for almost all graphs. In fact, he said something slightly more. He said that almost all graphs can be reconstructed from just 3 elements in the deck. So you don't even need the whole list. So that looks pretty good, and it's actually a relatively straightforward paper. It's not that complicated. And there's only a few graphs remaining, right? So, Brendan McKay, another computer type, using his naughty package, this is more recent, 1997, has shown that it's true for all graphs up to 11 vertices. Oh, and more than 2. Okay, so that's just computer search. But it gives you some kind of idea.
Certainly not such computer. Very challenging computer.
It's a pretty challenging computer search. I mean, you need to be pretty clever to. There's quite a lot of graphs when you get up this far. So, okay.
How many?
How many graphs?
Millions or billions?
Well, yeah. I mean, half the problem is you've got to work out about. You've got to be careful about graphs that are isomorphic to each other. You don't want to have to play the same game several times. So.
You have to be more than 2 to the 55th.
Yeah, so there's two to the yeah 2 to the n choose 2 is the number of graphs, but some of these are going to be isomorphic, right? So many of them, yeah. So the clever thing which Brendan McKay is able to do is to find canonical graphs which you can check, so you don't need to check all of these. Okay, so there we are. Right, now that's been that. Now the other thing in my title is modular decomposition. Perhaps I better tell you a little bit about that. Well, a module in a graph is a set M of vertices, which they're sometimes called intervals or clusters or clumps. They have many, many names, been discovered many times. Such that, let's say this, for all of x and y and m, the neighborhood of x, but I don't care about vertices in m, is going to be the same as the neighborhood of y, except vertices in m. So what this looks like is, here's m inside some bigger graph. I've got 2 vertices in here. If this vertex is adjacent to that one over there, then this one must be 2. And inside here, you know, there could be all sorts of things going. And of course, if it's not adjacent, necessarily it is also not adjacent. So they sort of form a little group, and they always have the same opinion of all the people outside of the group. And there may be conflicts going on within the group, but okay. Okay. So, if I take you can see that every single vertex on its own is going to be a module. It's always got the same neighborhood as itself. And indeed, if I take the whole graph, that's also going to be a module because there's nothing outside. Now, the graphs which have only these singletons and the whole graph as their modules, so they don't have any of these sort of proper modules in the middle, are called, well, I'm going to call them prime graphs here. So these have no proper, for some value of proper modules. Okay. Now for the graphs which aren't prime, there's something nice which we can say. We can take the maximal modules of this thing. So for non-prime graphs, so that means they've got some module. If I take the maximal modules, that partitions the vertex set, except for some special cases which I'll tell you about in a second. It partitions the vertices, and the structure of these modules, the way they're related to each other, happens to be a prime graph. So let me sort of show you what I mean. So here's a graph like that. There's a module. There's a module. There's one. There's one. And now if I sort of just colour in these things and turn them into super large vertices, I get the path of length 4. And that's a prime graph. And that's always true, except for disconnected graphs. But I don't really care about disconnected graphs. The reason why I don't care about disconnected graphs, maybe I'll show you why it's not quite true. So, for a disconnected graph, say I've got several components,